Welcome students once again into the class of number theory, and in this video we'll prove a very important theorem of number theory, that is fundamental theorem of arithmetic. Since we are doing divisibility, it is exactly a theorem related to the concept of divisibility. So let us see what is the fundamental theorem of arithmetic. So first write the name, that is fundamental theorem of arithmetic. What it says, fundamental theorem of arithmetic says that every positive integer greater than 1 obviously can be uniquely expressed as a product of powers of primes. So first write down the statement: every positive integer greater than 1 can be uniquely written as product of powers of primes. Before proving this theorem, I'll need two more results, which I'll name it as lemmas, lemma 1 and lemma 2. I'll prove two lemmas and then I'll use two lemmas to prove this theorem. So I'm going to rub it because I think you must have noted down the statement of this fundamental theorem of arithmetic, and now I'm moving on to the two lemmas. The results of these two lemmas will be needed to prove the result, this fundamental theorem of arithmetic. So the first lemma, let it be lemma 1. Lemma 1. Lemma 1 is, if A, B are positive integers such that their GCD of A and B is 1 and A divides BC, where C is another integer, then A must also divide C. If GCD of A and B is 1 and A divides the product of B and C, where C is an integer, then A must also divide C. This is our first lemma. First we will prove this lemma, then we will move on to this lemma 2, and after proving these two lemmas we will move on to the main theorem, that is the fundamental theorem of arithmetic. So let us prove this first. So what is the proof? Is very easy. Here we are given that A, B, GCD is 1. Therefore, by Bezout's identity, definitely there will exist integers x and y such that the GCD 1 can be expressed as a linear combination of A and B. So therefore, by Bezout's identity or Bezout's lemma, therefore by Bezout's identity, there exist x, y integers such that 1 can be expressed as a linear combination of A and B. And now multiply both sides by C. So multiplying both sides by C, what you are going to get, it is ACX plus BCY is equal to C. Now concentrate on the left side. One thing is clear, that A is here, so A divides this number. That means now A divides ACX. It is very much clear because A is a factor in ACX. And A divides BC. Why? Because we are given that A divides BC. And if A divides BC, then definitely A divides every multiple of BC. So A divides BCY also. So this and A divides BCY. Now A divides ACX, A divides BCY, so A must also divide their sum. So this means A divides ACX plus BCY. But what is ACX plus BCY? This ACX plus BCY is equal to C. So you can replace this ACX plus BCY by C. So A divides C. So we have proved that if GCD of AB is 1 and A divides BC, then A divides C. So first lemma is being proved. And now I am moving on to the lemma 2, which will be needed while we will be proving fundamental theorem of arithmetics. So the second lemma is lemma 2, which is nothing but the extension of lemma 1. If P is a prime, if P is a prime such that P divides n1, n2, n3 and so on, nk, where these n1, n2, n3, nk are n integers and P is a prime, then P must divide at least one of them. So that means then P divides nj for some j belonging to the set 1, 2, 3 and so on up to k. That means this nj is nothing that it is one among these. So nj may be n1, nj may be n2, nj may be n3, nj may be nk. So if P divides product of k integers where P is a prime, then P must divide at least one of them. So now I am going on to the proof of this lemma, lemma 2. Suppose this we will prove by induction. If k is equal to 1, then there is nothing to prove, because you will get from here P divides n1. And what we want to show, that P divides at least one of them. So P is dividing n1, which is one of these, and hence the proof is okay. So for k is equal to 1, we know that the proof is done. Suppose it is true, the result is true for k is equal to m. That means if P divides n1, n2, nm product, then P divides nj for some j belonging to the set 1, 2, 3 up to m. This is the second step of induction. And now move on to the final step, number 3. For k to be equal to m plus 1. Now look that P divides n1, n2, n3, nm and nm plus 1. Look this number as 1. If P does not divide this number, suppose P does not divide this number, then the greatest common divisor of these two will be 1. If P does not divide this product in the bracket, since P is prime, if P does not divide n1, n2, nm, then definitely GCD of P, n1, n2, n3, nm is equal to 1. Now let it be B and this is C. So P divides BC and GCD of P and B is 1. Just remind your lemma 1. P divides BC and GCD of P and B is 1. So P must divide C. So in that case your P will divide nm plus 1. If P does not divide this number, then we have proved that P divides nm plus 1. That means one of these numbers. Take the other case. If P divides this number, what will happen? If P divides this, if P does not divide this, we have proved the lemma is okay. If P divides this, then by the induction step, Just we have proved by the induction step, if P divides this, then P must divide at least one of these numbers. And one of these numbers means one of the numbers between n1, n2, n3, and nm and nm plus 1. So we have proved this lemma if P divides this number or P does not divide this number, and there is no third case we know. So the lemma 1 and lemma 2 are proved, and now we are moving on to the main theorem, that means the fundamental theorem of arithmetic. So fundamental theorem of arithmetic says that every integer n greater than 1 can be uniquely expressed as a product of powers of primes. Let there be a natural number which cannot be represented as product of primes. Let there be, we are moving on to the way of contradiction. Let there be integers, which cannot be written as product of powers of primes, or you can say product of primes, because powers of primes is also a product of primes. So let there be integers which cannot be written as product of primes. Let n be smallest such integer. Let n be, here concentrate on this smallest. What we have done, we have taken all the positive integers which cannot be written as product of primes, and since this set of positive integers, this is the set of positive integers, therefore by well ordering principle definitely there will be the least element, and that least element I have taken as n. So let n be the smallest such integer. So n cannot be written as product of primes. That means n cannot be a prime, because if n is a prime, then obviously n is a product of primes as a single factor. So we will suppose that n is not a prime. That means n is a composite number, and every composite number has a prime, has a divisor. Leave the word prime, has a divisor. So and therefore n must have a divisor. N must have a divisor. Let A divides n. Therefore, by divisibility, there exists some integer b in the set of integers such that n can be expressed as a into b. N can be expressed as a into b. Now, a is less than n, b is also less than n, because a and b are now divisors of n, and divisors of n cannot be greater than or equal to n, because n is not a prime. So divisors of n are definitely less than n, and n is the smallest integer which cannot be written as product of primes. That means a and b can be written as product of primes. A is a product of primes, b is a product of primes, and if a is a product of primes, b is a product of primes, ab must also be a product of prime. That means n is a product of prime. That means we arrive at contradiction. And why this contradiction? Because we have supposed that there are integers which cannot be written as product of primes. That means every integer can be written as product of powers of primes. So one part is proved, and now we are moving on to the converse part of this theorem. Sorry, not converse, uniqueness part. Uniqueness part of this theorem, that this representation of every integer as product of powers of primes is unique. So once again, let there be two representations. Let n be a number which can be presented at p1 power m1, p2 power m2, p3 power m3, and so on, pk power mk, and n can also be represented as q1 power you can say s1, q2 power s2, q3 power s3, and so on, qr power sr. Suppose n is an integer which can be expressed as product of powers of primes in two ways. So what will happen in that case? First of all, if p1 power m1 is there, You can write this P1 power M1 as P1, 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 P1 M times. Similarly, P2 can be written as P2, 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 P2 M times, M2 times. So this can be written as product of primes. So I'm leaving the powers now because I'm taking as that these P1, P2, P3 may also coincide. They may not be different. They may be, some of these are maybe same. So I have written N in two types in products of primes. Product of primes does not mean that I am neglecting the way product of powers of primes, because I am saying that these P1, P2, P3 they may be same. If P1 and P2 is same, then it will become P1 square and so on. So N is written in two different ways in powers of primes. So that means they are equal. P1, P2, P3, Pk is same as Q1, Q2, Q3, Qr, where P1, P2, P3, Pk, Q1, Q2, Q3, Qr, they are all different primes. May not be different, they are all primes. If there are some same primes, that means if some of the Pi's are coinciding with some of the Qj's, cancel them out. And write down the left one. Left one means now no Pi matches no Qj. If some are coinciding, I have cancelled out. I am left with a, because if all are coinciding, then this is unique presentation of N. Whereas we have supposed that the presentation is not unique. So if it is not unique, definitely some different Pi's and some different Qj's will be there. All Pi and all Qj same means the unique presentation. So here, since we have taken that this presentation is not unique, some different Pi's and some different Qj's, all primes, their product is equal now. Now note that this P1 divides P1, P2, P3, Pk. It must divide these. Now, this is same as the right hand side. So that means your P1 divides Q1, Q2, Qr. So that means this P1 divides the product of these are prime numbers. And we know that if P divides AB, then P divides A or P divides B. Or you can say if P1 divides the product of these R prime numbers, then P1 must divide at least one of these. So this means there P1 divides Qj for some j belonging to the set 1, 2, 3 up to R. So that means this P1 divides sum of Qj, but Qj is prime. And if Qj is prime, it cannot have factors other than 1 and Qj. P1 is for sure, it is not 1. And Qj is also not equal to P1, because if Qj and P1 are same, then they must have been cancelled out in this step. They have not been cancelled out means they are distinct. So Qj and P1 are distinct and one prime divides the other. It is a big contradiction. And why this contradiction? Because we have supposed that the presentation of N in product of powers of primes is not unique. So it must be unique. That means we have proved the fundamental theorem of arithmetic that every positive integer greater than 1 can be uniquely expressed as product of powers of primes. So it is very important theorem from point of view of your examinations. So I hope you must have understood this theorem. Write it down in your notebooks and wait for the next video. Till then, thank you. Thank you once again.